Okay, ครับ
Okay, so in the first half of this class, yeah, this is what we did in the first half, right? Basically, there are three kinds of machine learning that I want you to think about. One I call boundary learning, but this is not a standard terminology, so I'm not going to hold you to it, okay? But this is how I organize the algorithm. In other words, if you go to Python or mathematical library, they just list like 20 algorithms, okay? But in my mind, I organize those 20 algorithms into 3 groups, okay? So let's go. This is my categorization, okay? My categorization. Not universal, okay? So the first one is to say, I want to classify one data set from the other. So I want to separate things that are over here versus things that are over here. And things get complicated because you can have more things like this on this side as well, right? Okay, so basically I want to think of things that sort of, you know, can I do this? Can I do regression? No, maybe I can. Maybe I can do this again, and I can do this again, and I can do this, and I can do this, and something like that. So maybe decision tree would be able to do that. Okay. So the problem is I want to separate, right? Now, the first thing that we learned was to create one boundary layer, you know, some kind of boundary layer, some kind of magic boundary layer. Again, it's very hard. Oops. It's very hard to get this line like this. Okay. So most of the time, you can do things like, well, if you throw this problem to a linear regression, it's just going to give you this. Something like that. Okay. Right? If you throw this to a support vector machine and you are able to guess this line, you for some reason you are very smart, you're able to guess that it is separated by a quadratic function, say, okay? You can say that, oh, I can draw one function here, okay? And maybe you can use that function again here. But you have to really guess this shape right. If you don't guess this shape right, all bets are off. Okay, so this is what I mean by boundary learning. That's not very good. Okay, boundary learning. Okay, the other one is partitioning or cleaving or branching. So that's the thing. Okay, with branching you can do straight line because you can do it many times, right? Okay. So that's sort of like a sort of branching. So that's what we're talking about. Now, wouldn't it be nice? Wouldn't it be nice if we can have some kind of universal algorithm that somehow creates, okay? The word is create, okay? This line, oops, this line okay, without making any assumption. I don't need to know anything about this. I can just make this line up. Okay. Now, here's a video I want you to watch, but it's okay. It's going to take like a half a minute, so you don't have to stop the video or anything. So that is the video here. 2 minutes on. Well, first of all, let's look at this video. I'm gonna give you this in the notation anyway, so you're gonna have that. So let's go look at this video. Okay, I'm not gonna watch the whole thing. Okay, oops. Let me just freeze the picture here, okay? The idea is this, okay? This idea is called Fourier series, okay? So Fourier series. The idea is, okay, I'm gonna start fresh. I want to draw this picture, okay? I want to draw this picture. Okay, I want to draw this picture. Okay, but the only way I can draw it is using a sine wave. Here's what a sine wave looks like. Okay, a sine wave looks like this. So obviously, you know, if all I can draw is sine wave, I can't draw that. But let's say I can draw many sine waves and add them up. Add them up. Okay, I can add 5,000 of them. Okay, sometimes the peak will reinforce the peak, it will end up with big. Sometimes the peak will cancel out the other guy's peak, so it go to 0. So you can see that by adding this, okay, by some kind of magic, okay, if you have all the time in the world, okay, you can try different sine waves. You can try 5,000 sine waves of different frequency, okay. Remember the sine wave, you guys remember? Right? Okay. I want to plot sine wave minus pi to pi. Okay. And I want to manipulate n from 1 to, I don't know, 50. I don't care. Okay. Oops. Right. So I can do this, right? Now, imagine that I have 2 of them. Okay. I have 2 of them. Okay. Okay. Watch. See? So I can keep adding, right? I can keep, so if I keep sine wave, I can get all kind of funny behavior. I can also do this, add different amplitude. Right? Nobody's going to stop me. Okay. Right? I can get all kinds of shape. You can imagine that if I have enough time, okay? So the idea is this. Think of Fourier series. This one I didn't cover. I'm just gonna. This one I didn't cover. So leave that. Okay. Okay. So. I'm gonna cover this later. I'm gonna come back. Remind me. Oops. Neural learning. Okay. So I'm gonna go to, first of all, think of Fourier series. Think of Fourier series, okay? idea is that you can draw anything even enough sine wave. Okay, of carefully chosen of different carefully chosen frequency, amplitude, and also phase, but never mind. Okay, so if you have enough, and you can just add. Okay, you can draw and give enough of it to add together. That's the idea. Okay, now this thing is even nicer than that. This is in 2 dimensions. You can draw things in 3 dimensions. Let me see, what's the last picture in this video? Okay, if you think of a sine wave in 2 dimensions, it's a circle. Watch this. See, this guy is adding. Okay, let me write this. Think of 2D sine wave as a circle. You can draw 2D picture given enough circle. Okay. And this is the idea that you can draw a picture of, I don't know who this guy is, Beethoven, I think, right? This is, you can draw any kind of picture, and I encourage you to look at this video. It's quite amazing. Okay, you can just by choosing the right circle. All of this is a whole bunch of circle adding, right? So this circle, and at the tip there's another circle, and at the tip there's another circle, and at the tip there's another circle. If you have a whole bunch of them, you can actually draw a picture of a person. It's quite amazing. This is called Fourier series. Okay, so this is actually drawn using mathematics. Okay, so you can go to Google and say something like drawing Beethoven with Fourier series. Something like that. Beethoven, sorry. Something like that. Okay, and you see a whole bunch of stuff. Okay. It's quite interesting. Okay. Anyway, think of that. Now, think of our problem. Our problem is not trying to draw things. Okay, we're trying to draw this. You can use sine wave. You can use sine wave. But conversely, can I do this? What if, okay? What if I want to draw this again, but instead of having all the sine wave, I just have function that looks like this. My squishy function. I just keep adding them. Okay? Just keep adding them. If I need a lot of them, I just add them. Okay? The idea, so imagine instead of using sine wave or circle, use logistic sigma. Okay, now the key word is you have to have enough of them, right? So the idea here is given, so you can draw any function, you can emulate any mathematical function with given enough logistic sigmoids to add together. That's it. Okay, that's it. And watch this video real quick. It's gonna take 2 seconds, so I have to stop the video. It's this guy. There. Ready? Okay, stop. This is the function I want to draw. Okay, this is the function I want to draw. This algorithm is gonna add, but he doesn't use this. He doesn't use this thing. He doesn't use logistic sigmoid. He used this thing called ReLU function. Okay, it's basically a function that looks like this. Okay. Looks like this. Okay. So let me add that. Instead of using this, given enough logistic point, same thing. You can emulate any function given enough ReLU function. Okay. ReLU. Never mind. Okay. You can do this. The concept here is this, but the video I'm going to show you uses this. Okay, so that's why it's a different function. So don't worry. This guy is gonna try to draw a line like this or like this or like this. Okay, watch. See? So the first line looks like this, right? Straight line with a kink, except going from the left to right. Now it's going from right to left. So that's the first line. Add the second line. Add the third line. Keep adding, keep adding, keep adding, keep adding, keep adding, keep adding, keep adding. Right? Oops. Stop too soon. Okay, so let's go over here. You can see that by using 1, 2, 3, 4, 5, 6, he can already create something that looks really smooth. So can you imagine if I want to separate data that looks like this from data that looks like this? Okay, I can't do it with logistic regression. I can't do it with support vector machine unless I happen to guess, I don't know how, that the right function is this, which is a cubic function. In real life, nobody's going to give you the answer, so you don't know. So, but this guy doesn't have to know. He just keeps adding ReLU function, keeps adding this until it gets you a good fit. In this example, by the time you get to 6 of them, you're done. You get very good results already. Okay, so that's the concept. Now let's look at our concept. Same concept. Now using just 2. Okay, now this guy had 6, right? But he used a ReLU function. If he had just 2, okay, 1 is a logistic. So I'm gonna do this. I'm gonna do this. Now, if you recall, okay, logistic regression uses logistic sigmoid, right? So in a sense, we just want to add logistic sigmoid, logistic regression equations together. Okay. So let's see 2. If I add 2, okay, just now we saw this thing adding 6. Oops. Where is that? Oops, I just ended that. Sorry. Let me start again. Okay, so if I have just two, by adding them together, I already get this function. Okay, that's the essence. So already I'm getting some kind of curvature, right? I'm getting some kind of curvature. So you can imagine that if I have three, let's say I have an example with three. Yeah, let's have an example with three. Okay, right? I can create any kind of interesting function, okay, on the right-hand side. Now this, you know, I'm just making kind of random tuning there, okay? The point is I can create all kind of funny functions. Look at this function. Look at this guy. Okay, this guy, this, see, it's creating a wedge that, you know, some data can be in here or some data in that pocket and all kind of things. Okay, and I can use different function and all kind of stuff. Well, that's the whole point. Now this is the review, I guess, if you want to say it this way. The big review is, here's a big review. Your neuron is a logistic sigmoid function. Okay? And this is the biggest thing that you should, you know, when I heard, well, not I heard this, but the first time I learned of this, it's sort of like the jaw drops. Why? Why do I say that? Why do I say that? Let's go to the internet and look at the picture of a neuron. Okay, let's look at the picture of a neuron. This one's a good. I like this one. Let's see this one. Okay, this is a nice picture. Right, it's a nice picture. Yeah. Well. Okay. Anybody recognize this? This is a neuron, right? Well, this is a neuron cell. It has what looks like a root, okay, coming in. And then it has a long thing called axon. And then this then becomes something that attached to the roots of other neurons. So this is one neuron. This is one neuron. The way it works is this. Each of this is like a contact point. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, you have 20 input. Okay, so it's like, okay, right? You have 10 inputs. You have 10 input. Okay, input. Okay, let's say, okay, this is your input. Okay, look at this picture and look at this picture. The same thing. I have input, 20 of them. Now the signal comes in. It gets multiplied according to the chemical inside the branch. So sometimes you get amplified, sometimes you get decreased, sometimes you get just a small amount. Okay, so what exactly is the multiplier? That's my multiplier. So by the time I have 20 input signal multiplied by 20 coefficient, what do I have over here as a summation? I have input dot weight, right? So this is nothing more than a weighted sum. Input 1 multiplied by weight 1 plus input 2 multiplied by weight 2 plus input 3 multiplied by weight 3, okay? Right? So let's make it a bit nicer. Just make it 5 maybe, that's easy to see. Right? Okay. See? Input 1 times weight 1 plus input 2 times weight 2 plus input 3 times weight 3 plus input 4 times weight 4 plus input 5 times weight 5. Now, once it gets over here, this is your signal strength. Signal strength. This is your signal strength. Now, there's some kind of threshold to overcome. And this is what happens in your neuron. Your neuron has some kind of threshold. Threshold is equal to, I'm going to call it theta. Threshold. Okay? So theta. Right? So, and then, okay, if the signal is stronger than theta, okay, if signal strength is greater than theta, fire meaning shoots a signal to the neuron, okay, lights up. If not, otherwise, stay. Right? If signal is greater than this, fire, otherwise stay quiet. What do I mean by staying quiet? I give 0. What do I mean by fire? I give 1. Now, have you seen some function lately that gives you something that approaches 1 based on some condition? Obviously, that is logistic sigmoid of signal strength minus theta. That's it. That's it. And the signal strength, so if your signal strength is weight times, so if, in other words, your neuron fires logistic sigmoid W dot X minus theta. That's what it does. Okay? That's what it does. That's what the neuron fires. So if you have your brain, so the first thing first, a lot, okay? First thing first, logistic sigmoid is equal to neuron. So logistic regression can do what an animal with 1 neuron in the brain can do. Okay? Now, what's a neural network? Artificial network of artificial neuron. Okay, so a logistic one is equal to 1 artificial. Okay, logistics. So, i.e. use logistic sigmoid to mimic the working of one artificial neuron. The side comment is such. Okay. Artificial neural networks is a network of artificial neurons. And now, this is why I asked you to watch the video, this guy. Okay. Okay, done. Okay. What this function does, oops. Okay. Okay. Oops. Let me stop. I'll say a little bit. Okay. Instead of having 20, in this case, this dendrite has dimension 784. It just happened to be in this case. Okay. All this is like this. What's the picture? Let's see. 1, 2, 3, 4, 5 up to 784 is like this. Okay, except instead of having just 20, this guy has 784. Each of them multiplied by the weight in here, blah, 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 goes this one. Inside this one, it looks just like this. In other words, inside this one, there's a threshold. You sum it, and then you take the threshold, you subtract from it, and then you find the logistic sigmoid. So here, sometimes when you see a neural network lecture, you see something that looks like this. And then there'll be a symbol, something like, okay, something like that. Okay? In here. So that's one neuron. This is a bank of neurons. This is another bank of neurons. They don't call it bank, they call it layers. In this architecture, because it exists in a layer. Now, your brain is not organized, strictly speaking, in this kind of definite layer, right? Sometimes you have this neuron connected to that neuron. But the first approximation is what's called multi-layer perceptron. So, oops, write that note now. Okay. Big review. Okay. So if let's call such an artificial neuron a perceptron. Okay. Then put bunch of perceptron together into a layer. Put a few such layer, okay, in sequence. Then you have multi-layer perceptron. There's no S. Yeah. So that's it. That's it. That is multi-layer perceptron. You can think of it as a multiple, which you can think of as multiple sequential processing stacks or parallel processing artificial neuron. Okay. Now, why does this work? This work, okay, just like with Fourier series, this is quote unquote guaranteed work. And the mathematical theorem that proves is this thing. Universal approximation theorem. Okay? Universal approximation theorem. So this is guaranteed to work. Now I'll show you what the picture. I think I have the original picture. Sorry, the original paper. And the seminal paper. There you go. This picture is critical because it proves that you can do this. Why is it important today? Because at one time, okay, at one time, now you guys grew up in the age of AI, but at one time, people were going to stop researching artificial intelligence. Literally, there was this thing called AI winter. You know, in English, winter usually means something like starvation. There was a big AI winter, meaning people who were into research were going to stop researching AI altogether because they think that AI can never approximate human being in the logic. Well, it takes a couple of hurdles to overcome. One of it is this paper. Okay, this is one of the seminal paper that makes everyday life possible today. It's saying that if you have enough sigmoid function, you add them, you can approximate anything. And this is called universal approximation theorem. And because of this, you can say indirectly or directly, the funding for AI research did not stop. Government continued to fund AI research, and the AI research continued long enough for the computational power to catch up. And then we have today. Okay, so this is really wasn't at one time, you know, it used to be a make or break moment. Okay, make or break moment. Now, I want you to then go and watch the, you know, how neural network learns and so forth. But the basic idea is simple, okay? Now you can see that with just 3 neurons, I can already make complicated function. That means I have just 1, 2, 3. Imagine I have 20 more. And on top of this, I have another layer, I have another layer, I have another layer. Eventually, when you have many layers, okay, you earn the name, the title, deep learning, okay? Well, you actually have something else, but you know. The reason is, in the old days, like when I was your age, for example, we can only do like 2 or 3 layers, okay? Like something like this we could do when I was your age, okay? The world could do something like this, maybe 5 or 8, 10 layers. But beyond that, you can't. You can't. The computer doesn't do it, and the algorithm sort of like stops working. There's this thing called vanishing gradient. You may not, you don't need to know about it now. But basically, if you keep adding many layers, the model stops tuning, stop readjusting. Remember, I told you that machine learning is about algorithm to adjust the parameter. Well, if you have so many layers, like 10 layers, the parameter just kind of stay there, doesn't do anything. So even if it gets an error, it doesn't change. Look at today's architecture. Let's go to picture. Let's go to something like Wikipedia, okay? Let's go to something like deep learning architecture. And let's go to picture. Okay. This is what you do today. Let me show you. Let me show you what a typical architecture looks like. nowadays. Okay, now this looks like nothing, but this is the notation, guys. This is actually one layer. Oops. 11 weight layers, 13 weight layers. So altogether, this architecture has 11 plus 11 plus 13 plus, nearly 100 layers. Okay, you have all kinds of stuff. Google Net. Now, this is the picture I wanted to show you. This is the sort of like, each one of this block is already bigger than this. It's already bigger than the picture I just showed you. Okay. This thing, this kind of multi-layer perceptron, let's show it by contrast. Multi-layer perceptron. Okay, it looks like this, yeah. It literally, when I was your age, we were working with something like this. Okay, something like this. Okay. Now, imagine each one of this is already much smaller than what's inside here. And then you have so many things. That's why this is called deep learning. It's many layers. Okay. Yes. Something else. Okay, no, I'm not going to. So, if I were to do this as a sort of like a taxonomy, okay, let's go to this picture. Okay, something like this, machine learning. Okay, and I call this supervised machine learning. Okay, and call quote boundary learning. Okay, call this learn matching. Okay, call this neural learning. Okay, it's going to look like this. Neural learning is basically ANN. ANN is the biggest word here. Okay, it's so ubiquitous, people don't even say that anymore. Okay, so you can have MLP and then deep learning. Then you have whole bunch more. Etc. Boundary learning, okay, linearly comparable. Anyway, okay. So this is okay. So think of it. So that's where we are. That's where we are. Okay, that's where we are. Now, I want to show you final thing. Final thing. Okay. This thing called functional link net. Okay. Let's go back to functional link net. Well, remember I told you that with enough neuron, you create any kind of function, right? But if you think about it, just like when you work with, say, support vector machine or nonlinear kernel, sometimes you wanted to, sometimes you wanted to help with basic function like x squared. You can do that. You can add or x1 times x2 or, to incorporate interaction, something like that. So instead of just putting the raw x, you can put in some kind of basic function. I call that mathematical primitives. So instead of having this thing where, okay, where this is x1, x2, and x3, and x4, maybe I'll add something like x1 squared, x2 squared. You see what I mean? Because universal approximation theorems say, eventually, if you have enough of this, if you have enough neurons, you can create x squared, x cubed, x4, you can create anything. But you know, why waste a whole bunch of neurons if you kind of want to jumpstart the process? You know, instead of just giving you x, just give it x squared to begin with, because it's gonna save you a whole bunch of neurons to do that approximation. Think of it that way, remember? Because just now you saw that that cubic function takes a whole 6 neurons. Now, if I already add x, x squared, x cubed, I don't have to have 6 neurons over here, right? That's the idea of functional linear. Let me show you how it works. Let me show you how it works. Now, this is kind of like very special to me because my very first professor in neural network was a pioneer in functional linear. Okay, he's probably in his 90s. Okay, so think of it this way: this is your x1, this is your x2. Okay, let me blow it up a little bit. Okay, now the objective function here is I want to separate the blue from the orange, right? And let's say I have one final output for blue, one for orange, or whatever, and I have 4 neurons in between. Can I do it? Yeah, I think I can. I think I can. Let's try that. And this is called this is a simulator. Okay, where's the play button? There should be a play button. There, play button. Okay, so that's not difficult. That's not difficult. That's kind of completely doable. Well, it's a bit harder if you have less. Yeah, it's kind of hard. Now, imagine this, yeah? Imagine that you don't want to add neuron. I just show you that if you add neuron, it works, right? Right? I can create function. By the way, this is x1, x2. So that multiplied by the weight. The weight is 0.52. The weight is 0.61. The weight is -63. And this is a neuron. That's basically logistic sigmoid function. And there's another weight. So you can click all this and see. Okay. So this worked. But going back to what I was talking about earlier, I don't want to have. Oops, sorry. Okay, let's say, okay, let's do this. Okay, now I can add the middle layers, and I can do that, right? But I don't want to do it. I want to save on neuron. Neurons are expensive. Instead, I can just add something like this. You know, x1 squared, x2 squared, or x. Okay. Now these are really cheap because you can do Excel multiplication on that, right? There, see that? See that? In fact, I don't even need all that. I think it's just, see? And this is called functional link net. This is called functional link net, right? It gives you the power. And this was very important, especially in the days when computer was very expensive, okay? Nowadays, people pay less attention to do this. They do something else. Instead of putting in x1, x2, x12, x22, they will put something else over here, like convolutional filter. They will put something like, you know, NLP embedding functionalities, auto encoding. They put something else here, okay? But this is the simplest way to show functional link net, right? See, so by using, I think you can just need one neuron. Can I do one neuron? Let's try this. Yeah. In fact, remember I told you about the reason I think that support vector machine is not useful, because you have to know what this line is. If you can guess correctly, you can do that. The point is with functional linkness, you guess the primitives. You don't guess the kernel entirely. You guess the primitives, and the model adds the primitive. That's the difference between using nonlinear kernel with support vector machine and using functional linknet. With functional linknet, you add simple stuff like, you know, x or sine function or something like that, very primitive function, and play with it. Play with it. Let's try this. I'm just. It's a bit weird, but certainly can do that, right? Again, with 2 neurons, you can manage it, but you cannot manage if you don't. So there's still a little bit of error here. If you add this, definitely maybe. Okay, you get the point. Okay, so this here is x1, x2, x12 here is not the third one. It's x1 squared. Okay, and this is x1, x2. Okay, so this is functional links. All these here are functional links. Okay, functional links. And this is the area under the curve. Right. So I think that's pretty much where we are. So if I have this, you should have this kind of schematics in your head. I can give this to you, just, you know. So something like that. Logistic, regression, or linear kernel. The point is, you can also have this as well, right? Learn branching, so decision tree. Okay. How about this? I call it some kind of tree versus forest. Okay. And then you have some kind of decision tree. You can also have regression tree, where instead of just separating, you can separate condition on regression. Random forest. Okay. 1, 3. More than 1, 3. At random forest with gradient boosted tree. Okay. Yes. Now with deep learning, then obviously there's going to be a whole bunch of things in here. Okay. So multi-layer perceptron, there's also just strictly feed forward. So okay. FFN. Forward. And then this can have some kind of recurrent. Yeah, all this stuff. Let's say I'm going to put this under classic. Yeah, classics and deep learning. There are other feed-forward that's not multi-layer perceptrons. What this means, what recurrent means is this. Instead of having this thing go forward, it can go back and feed itself. Okay, so like a feedback loop. Now with deep learning, okay, I separate into a few families. With deep learning, there are actually 2 things. Okay, by family of function, by super architecture. Okay. Now, by family of function, for example, you have, oops, by family of function. CNN. I'll give the name to you guys, sorry. Recurrent neural network. Okay, this is a feed forward. Okay, MLP is a little bit like that, except MLP is multi-layer acceptance. Okay. And then you have something like regular, classic. Then you have functional. Sometimes they use SLMN, right? This is SLMN. Okay. Okay. Let's see. Okay, and like that. Now you have this family of CNN. You have family of short. And you have some kind of stuff, and then you have other things. But let me see which one. Where did I put it? Types. Come back. Okay. Okay. So CNN is a family. Now this thing is the one that I'm talking about by super architecture. Super architecture meaning that GA Chinese, all kind of stuff. This is something like well, I'm not going to cover that right now. Okay, but this is where you see things like this in your iPhone. Neo Neutron. I'm gonna put Neo Neutron first because that's kind of like the precursor. Neo Neutron. So see this in time series model. In other words, there's a memory kind of thing. See this in image. Let's see. Okay. See this a lot. See this. Okay, and this thing you still see a lot in certain. Okay, you see this in deep fake, all kind of stuff. Let's see. Yeah, I'm not gonna go. Okay, I'll take it to my. I'll give you the name. I won't cover them all. Okay. Okay, it just gets huge. It gets huge. The key feature about deep learning is not really, deep learning is essentially artificial neural network, but you couldn't do it before, computing power capability. Okay. Well, oops. The classic, I'll call it classic, I guess. I don't know what to call that. Or you can say something like pre-2000s. And that makes it sound old. Okay, but that's the classic. So that's it. Supervised machine learning, unsupervised machine learning. Okay, and then reinforced machine learning. Put the sheet here. And sometimes all this thing is put here. Now, in my categorization, there's actually representation, and I will put this over here. We actually put this over here, but some people traditionally it's 1, 2, 3, and this thing is over here. And I put something like that. So that would be my categorization. Okay, and this again, you have plenty of things we did before, right? We something like a clustering, dimensional reduction. Okay, and then this, you get encoder. So this yeah. So okay, something like that. Then we can use the feature map and okay. Enforcement learning, okay. Q learning. Okay, so all these are things that if you go to apply digital intelligence track, you probably play with at some point. Now, because we are in this class, we'll probably use something like let me just put a okay. Strings use that. We use this as well. Okay, use this as well. One of you guys are doing this, bird, right? Okay, bird family. So this one we want, this one we want, this one maybe, but most likely this guy do. This guy do. Definitely this guy do. all this you can do. This one maybe, if you like. Okay, so that's it. That's the machine learning. Okay, now I can go into any of these, right, and then expand the concept and many things I don't even know. Okay, many things I don't play with personally. I don't have experience with personally. Ensemble, certainly I use that a lot. This one I haven't really used that much, a little bit. Okay, right. Okay, the classics. I'm just gonna. Yeah, HowFieldNet is also very good here. I'm just gonna do like this. Okay. Latent boosting, maybe something else. Something else. Okay, the reason I add to put that something else is, so you don't get the impression that this is everything. Okay, so that's very much what I wanted to cover for today. Okay, now I want to spend like 15 minutes or maybe 5 minutes, sorry, on the project pipeline. This here, I think the idea, again, I want to emphasize, let's look at the class note from last time. Document, you guys. Class notes. Okay. Okay. Now this thing is about your project here. Okay. The methodology. I just want to add to this. That in the way you do your pipeline, the concept is notion pipeline. It's like, if you think of you know what a pipe is, right? A pipe is thing for your water to come in. In this case, we're talking about clean water. We're not talking about sewage. Okay. But once you have the water comes in, it goes to that room, it goes to this room, it gets boiled, it adds this. So you can think of it as a flow. Okay. So it's like flow of information from data is from raw data. Now, raw data is when, for example, we look at some experiment that, from raw data into some kind of clean data. Now this would be some kind of cleaning, okay? Then from clean, okay, to some kind of pre-process. Okay. Now example. If your clustering analysis is not scale invariant, right? In other words, if x1 is in 1,000, x2 is in 100, okay? Clustering will just separate along x1, right? That's common sense. So you need to do some kind of scaling. Okay? So this is kind of pre-process. Now, from pre-process, this is sort of like, this is not your workflow. Your workflow would start let's say I have a workflow, right? You get data, you get some kind of visualization, and some hypothesis, and all that, right? So this is not, this is about, at the end of the day, your package would, this is how the program flow, let's put it this way, okay? So from pre-process to optionally and feature engineering. Now this is done a lot in practice. I don't like this practice, but people do that. And sometimes it is useful, and I do use that. Okay. In other words, sometimes you have some kind of insight from business that X1 is not useful, but X1 divided by X2 is, or something like that. Okay? Or X1 is too noisy, so use moving average. Okay, so X1 of T, something like that. Yeah, sometimes this helps. Okay, and then of course the main key analytics. Agi say supervise machine learning algorithm. Okay. Now, before you get to this, you have to obviously partition data, train versus validation versus test. I haven't told you what validation is, but I'll come back to it next time. Say something like that. And then you keep, so train test. This is kind of a result. Okay. You want to do what? You want to do two things. You want to present and result as a with a table with visualization okay, performance, say something like accuracy. Now we talk about everything, right? Confusion table, you know, all kind of stuff, right? So it's a model performance. Okay, with visualization. The other thing is as a tool. Apps. You guys like using the word app, right? Okay, as a competition. Okay, so you will run through this all the way to here, right? All the way to here. This would be like you write a program, you generate the table, you generate the result, and then this is how you present your results, right? The result would have to come from this. So this is sort of like an input phase, So this, you can think of it as 3 phase. Input, one, okay, and then I would call this 2 is the main thing here, and then 3, something like that. I don't need to. Right. What I would like to do is now I'm going to assume you have, I've looked at some of the proposal. You have idea of the data. Okay. Homework. Okay. Homework is to download data and then do some visualize. Okay. I don't know what your data is. Okay. So whatever, histogram, scatter plot, basic statistical test, normality, or some kind of correlation. Okay, whatever. You guys know what a stationarity is? Memorize. Okay, so that's yeah. So the homework would have 3 sections. 1, describe the source and the data itself, size, okay, some kind of meta data, like it's a say description. 2, visualization. 3, what you think you can do. In other words, we're talking about here, okay? What you can do. Okay? Or plan. Do. Yeah. Perhaps you can relate it original goal. Okay. So for example, your original goal may be to predict Y from X, but then you look at your data set and you realize that Y is incomplete or X is not complete or something like that. Then you have to think about what to do. Maybe you can do something else. You can't predict. You can characterize. I don't know. Okay. Maybe perhaps okay or not okay. This is original goal. Original goal, previous homework. Okay. That's it. So this would be, I don't know what number homework. I think this is number 5, if I'm not mistaken. Okay. So if that's number 4, yeah, maybe something like this. And okay. Finally, I'll give you guys something of a to play with, and this I think I just okay. Now, you guys remember, right? This is a I literally made this example this morning or this morning for you guys. It's basically the example I use in class, except instead of wearing trouser, which is a binary event, yes, wear trouser, no, do not wear trouser. This is like a cute continuous number. Continuous number here being height. So I'm gonna, based on this, okay, I just made up some example. Let's say that this is the height of the population. The height population consists of male and female. And I'm going to make some kind of assumption, you know, this is my assumption. So this is proportion of male is 48%. They usually are less male than female, apparently for the humanity, history of humanity. So let's say we have, so we can move this around, obviously, okay? So this is the male, it's the blue, female is this. And based on my assumption, I'm just making up some number. Males are a little bit taller, right? And a little bit higher variation in height. So 1.64 meters, let's say, with standard deviation of 12 centimeters. And female maybe 1.6. I'm just making up some number, right? So you can see that here, this population is a mixture. So if I add more male, I can add more male actually. But I just make it at most equal. Okay? But certainly I can make male less. So you can see that the relative size of the yellow versus blue. But let's go back to the original setup. I have set equal to 1.48. Now the idea here is this. Instead of saying, what's the probability of male given wearing a height? Okay, we have this, right? We have this finally. Probability male given trouser. Yeah, I'm going to change it into height taller than red line. Yeah, that's what I'm doing. Okay, so this is my red line. If you go through this, there's a lot of silly formatting. Basically, this is my probability male, this is probability female, this distribution male, this is distribution female, right? I am going to say above this line, there's a probability, so this is all the conditional. There's a probability male, okay? There's a distribution, probability tall given male. So this is something like tall. It look like this in the note. Even male, okay? This is my notation. So probably tall given male, right? Okay, it's that male, taller than theta. Probably female, probability tall, okay? And then I make this probability male given this is this, probably tall given male, male given tall given male, male tall, right? And then I calculate. So this is probably tall given male, probably tall given female. But the key inversion that we show in the Bayesian theorem is I want probability male given tall. Notice if okay, so notice that I make this red line. It happened to be the intercept of this curve, but that's just coincidence, okay? The point is, right now, if somebody is taller than 1.68, I'm going to guess it's a boy. And that probability is 61 to 39, or 62 to 38. So the odds are it's going to be male. Now, as I make this higher, okay, I make it tougher. I'm going to make less false positive, right? See, the proportion goes up, 66 to 633. Keep going. 69 to 30, right? So if I run into somebody over 1.8, I'm going to make an assumption that this guy is a boy. I'm going to have a 78 to 22% odd in my favor. Okay. Now, this power is going to give you what? A lot less false positive, right? But it's going to be a lot of false negative because there's a lot of male down here as well. So let's go the other way. Let's lower this to here. See? You notice that even down to here, okay, over 1.6 is still probability of more males than female. It's only when you get, say, let's say lower, a bit lower, a bit lower, a bit lower, It turns out that it's only when you get a little bit lower. Okay, yeah, okay, let's stop here. Oops, sorry. It's only when you get to this point that probability above this line is more likely to be female. You know why that is? Because female have higher probability, right? That's the prior, that's this guy, that's 1.48. 1 minus 40.48, that's 0.52. In fact, if I just go all the way to here, okay? Notice probability male given tall and female has nothing to do with being tall or being short. It's just the fact that there are 48 male to every 52 female. So when I go to this way, I'm not making any discrimination, right? So obviously that's a bit silly, right? So normally I want to do something. I want to make some kind of surety, okay? So don't worry that this thing happened to intercept precisely here. Maybe that's a little bit misleading. So let's go lower to 1.65, okay? Yeah, okay. So you don't focus on the fact that it intercept. That has no significance. Okay, that's no significance. Okay, so this would be something like an example of using Bayesian. Okay, using Bayesian to do this kind of analysis. So that is really the prediction model. Okay, in fact, this separation is like a Bayesian tree. If you think about it, I can separate this tree using anything, right? I have a tree structure. Where's my tree structure? It's a decision tree. There's also regression tree, and there's also Bayesian. It's a little bit like what we did here, except instead of having one cut based on height, you go to the next cut based on weight, you go to the next cut based on hair length, you go to the next cut based on body mass index, okay, or whatever, okay? So this would be something like you can do that as well. So Bayesian belief network is also very popular. Let me give you a very nice Bayesian belief network. So stat quest. This one is it's very easy to understand. This guy's a bit funny. Okay, naive Bayes. Okay, that's good. That's good. I'm just gonna leave this up. Okay, that's not here, but this guy's here, and this one is only 15 minutes. Okay, so that's that. That's all I need to do. Okay, so you guys have any question about the homework? Assuming I will assume we already have fairly precise idea of data use homework 5. Okay, so that's what I want to do. So I'll give you this to play with as well. This is the inversion that's happening. This is the Bayesian inversion. This steps here. Okay, let me save, let me close, let me save, let me close, and this is the last one. I don't need to close that one. Do you guys want this as well? This is a diagram. It's not really. Okay,ครับ. So I'll see you next week. Now, next week, I want to do things differently. I want you to, I'm going to randomize maybe just 5 of you to present what it is you want to do. Okay. From now on, we'll pick maybe not 5, I don't know, 10 or whatever. Okay. Some subset of you to discuss your project to start there. So in the beginning of class, I'll pick up randomly, say 5 names, maybe 10, I don't know. Okay. And then the next class will be another 10 or another 5. Okay. To talk about where you are in your project. Okay,ครับ. So I'll see you next Tuesday. Okay,ครับ. Unless you have any question, more than happy to. Okay,ครับ นัท
Thank you
จบได้ครับ